We'll return back to 1770 and look at what Leonhard Euler said. At the time, mathematicians have tried in vain to discover some order in the sequence of prime numbers, but we have every reason to believe that there are some mysteries which the human mind will never penetrate. Okay? And 30 years later, here's a quote from Gauss. The problem of distinguishing prime numbers from composite numbers and resolving composite numbers into their prime factors is known as one of the most important and useful in arithmetic. All methods that have been proposed thus far are either restricted to very special cases or are so difficult that they try the patience of even the practiced calculator. The dignity of science itself seems to require that every possible means be explored for the solution of a problem so elegant and so celebrated. Wow. So these two great thinkers have really set the stage for the challenge ahead of us. And now I'm going to fast forward to 2010 and show you a paper that came out of the RSA competition, which is a competition that no longer runs, but the purpose of the competition was to put out a large number and say, can anyone factor it? So in 2010, this winning team factored a 768-bit number, and that means it was a 232-digit number if you're thinking in base 10. So this team in 2010, they won the competition by factoring a 232-digit number. So that's how far we have come from Euler to, or we can go back to Euclid, but from Euler to 2010, we're at 232-digit numbers. And here was the answer in their paper. So this was the first prime, this was P1, and this was P2. So this is the state of the art right now. Okay, how did they factor this number, and what is the state-of-the-art techniques? Well, we're going to go back and build from the beginning. And this kind of defines computational number theory. That is the topic of this adventure. So what does computational number theory mean? Well, computation comes from the Greek word for gravel. Stones were used for counting. Computation is any type of calculation, whether you're using stones or a ruler or a slide rule or a calculator or this cool looking machine, which is Babbage's difference engine, which was a hand-powered calculator. It doesn't matter what you're using, or you're using a computer. You're doing some sort of computation. And now, what kind of computation are we doing? Number theory. And that involves this mysterious distribution of prime numbers. Studying this distribution, and what we're actually looking at is multiplicative number theory, which is questions of how do you factorize numbers, how do you tell me if a number is prime, and so forth. And we begin with a very simple question, or not a question, a challenge. We need to build a machine which takes an input, and that input is some integer x, and all that machine needs to do is output true or false. And that is the first step. Now we will use the computer science tool to actually build this machine together. And one of the questions that we will be asking is two aspects to this machine. How much time, that's a clock, how much time does it take to give the solution? And how much space does it need? And when I say space, I mean, in the case of this mechanical calculator, physical space. How many rooms do we need to hold our machine? Or if we're using a computer, how much memory does it need? So we will be returning to these two ideas as we go.